Good afternoon, ladies and gentlemen. In the following minutes, I will introduce the result of the, should be this one, decadal prediction by using LASG LASG model. And here is an outline for my talk. First is the introduction of the model and also the initialization schemes we used. The model we use here is the LASG S2 model. It's a standard version for CMAP5. For the atmosphere, we have a 2 by 2 degree. For the ocean component, we have 1 by 1 degree, but we have a local zoom along the equator. Please note here, in the EGCM component, we treat the radiative effect of volcanic aerosols were considered by changing the stratospheric aerosol optical depths. For the design of the initialization scheme, we use the so-called IAU scheme. For the observational data set of the ocean, we use the Met Office Graded Objective Analysis Data version V2A. We have used anomaly assimilation approach, so there is no treatment of the bias correction in the post-analysis. This kind of IAU method is designed for the data assimilation system of meteorology and then applied to the ocean assimilation and later used in the coupled model initialization. For the design of the Handcast, we follow the CMAP5 protocol. We have done 10 years long Handcast and forecast, and we studied every 5 years. We have performed 3 ensemble member simulations. To measure the scale of the Handcast, we used the root mean square scale score developed by France. This is also the method used in IPCC AR5 report. How about the result of this kind of Handcast? Here we have used the following metrics to assess the model's performance. The first is the root mean square scale score of the surface air temperature. The second is the scale score of land precipitation. And the third is the global mean surface air temperature time series. The fourth is the Atlantic multi-decadal variability. The fifth is Atlantic meridional overturning circulation. Please note here, actually, in observation, we do not have observed amok, so we used the amok derived from the ocean reanalysis. And we also checked the scale in the simulation of the IPO, or called PDO, or somebody called mega ENSO. First, how about the scales in the surface air temperature? Here I show the scale for the forecast time of 2 and 5 years and 6 to 9 years. And here is the ratio of the root mean square errors. You can find in both 2 to 5 years and 6 to 9 years, we have skillful predictions in the choppy Indian Ocean, Western Pacific, and the North Atlantic. These kind of patterns are evident in both the 2 to 5 years forecast and also the 6 to 9 years forecast. Here I also show the result of the multimodal ensemble of CMAP5. We can also observe high scales in the choppy Indian Ocean, Western Pacific, and the North Atlantic. Similar stories can be found in the root mean square errors. So for the scales of FGOES is nearly the same as the multimodal ensemble of CMAP5. Of course, FGOES model is also used in constructing this kind of multimodal ensemble. In CMAP5, there are 15 models used in doing this figure. The second is the scale for the land precipitation. You can find different to the surface air temperature, the scale of the land is pretty low. Here, I also show the result of the multimodal ensemble of CMAP5. You can find the scale is better than FGOES, especially over the higher latitude. But in comparison to the surface air temperature, the scale in precipitation are pretty low. How about the global mean surface air temperature? Here I show the correlations between observation and the handcast for forecast time 1 to 4 years up to 6 to 9 years. And here is the root mean square errors. Here are the results for the multimodal ensemble of CMAT5. You can find in CMAT5 the correlations are stable. In AppGoes, however, the scale has increasing following the increase of the prediction time. This is the difference between AppGoes and the multimodal ensemble of CMAT5. Here is the global mean surface air temperature for the non-initialized simulation, initialized handcast, and also the observation. I also show the result of the multimodal ensemble of CMAT5. It's not surprised to see we can find the initialized handcast show a better result than the non-initialized simulation. How about the Atlantic multi-decadal variability, AMA? Here, again, I show the correlations at different forecast time. Please note here, the red is for the initialized handcast. We do find better result in comparison to the blue line. And again, here are the results of the multimodal ensemble of CMAT5. The story are nearly the same. If we compare the root mean square errors, we can find the initialized simulation is better than the non-initialized handcast. This is the case for AMA. We also show the AMA time series here. Again, the blue is for the non-initialized handcast. The observation is here, and here is the initialized simulation. It resembles the observation. The result is better than the blue line. And again, here are the results of the multimodal ensemble of CMAT5. We can find nearly similar stories. How about the amok? Here, please note, as I noted before, because we do not have observed amok time series, so we follow the method by Xiaosong Yang from ZFDL. We use the amok derived from the data assimilation as the so-called observation. And here is the correlations between the handcast and so-called observation at different forecast time. You can find the red line in comparison to the non-initialized handcast. The initialized handcast do show better result. There are significant correlations at forecast time 1 to 4 and up to 6 to 9. Here is the time series of the amok time series for the at forecast time at 6 to 9 years. You can find the black is here is the so-called observation derived from the data assimilation, and the red is the initialized handcast. You can find it's far better than the blue line, which is a non-initialized result. Another question is, where does the scale of the AMA predicted come from? Here, I show lag correlations between the AMA time series and the northward heat transport in the model at different lags. You can find, especially at lag 2, that means 2 years after the heat transport maximum, we have the largest correlation here. So based on this, we can find the scales of the AMA prediction in AppGoes actually comes from the prediction of the amok in the model world. How about the IPO or PDO? We first compare the PDO mode in the model world with the observation. Please note here the model we used, the model data actually is a historical run, not a decadal prediction run. If we compare the patterns between the model and the observation, you can find the pattern of PDO in the model world resemble that in the observation. That means the model shows reasonable result in the simulation of the PDO mode. How about the handcast scale? Here, I show the correlations between the handcast and the observation. You can find actually in both the correlations and the root mean square areas, we cannot observe useful scales in the handcast. We have another set of simulation. Here, we use another model. Please note we changed the EGCM from Samir to another model is a grid point atmospheric model, but it has a low resolution. One difference in this model is that we treat the radiative effect of volcanic aerosols by changing the solar variability. That means we do not specify the changes of the aerosol optical depth in the stratosphere. But for the initialization scheme, it's exactly the same as the F goes S2. How about the Handcast result? You can find here is the correlations of the 10-year mean sea surface temperature predicted by this low-resolution model. You can find now we have less scales in the North Atlantic, but we do have positive scales in the Eastern Pacific. So this kind of difference suggests scales of the decadal prediction are highly model dependent. These two models share identical initialization scheme, but the Handcast scales are far different. How to understand this kind of difference? Here I show the global mean surface temperature in this low resolution Handcast. The red is the initialized Handcast, the blue is a non-initialized Handcast. You can find in this stage we do have something like a heaters in the Handcast. I think maybe part of this kind of scale is due to the skillful prediction of PDO in this set of Handcast. But for the low scale in the North Atlantic, here we compare the result of global mean is a mean state of the Atlantic meridional overturning circulation. In the higher resolution model and the relatively lower resolution model, you can find in this model the Atlantic meridional overturning circulation is too weak, far weaker than F goes 2. This may explain why in the Handcast by using F goes GL, we have low scales in the North Atlantic. But for the low scale of F goes S2 in the tropical Eastern Pacific, we do not have a solid answer. We hypothesize that it may be due to the treatment of the aerosols. Maybe this morning, the idea posed by Jerry may be one answer for this. That means if F goes S2, the response of the model to volcanic aerosol is wrong. Last, I want to note the low scale of the PDO Handcast actually pose a challenge for the prediction of the global monsoons. Here I show, yes, the green is the PDO index, covers the past 50 years, and here is the East Asian Summer Monsoon Index. You can find in the past 50 years, the evolution of the monsoon is just out of phase with PDO. We further extend the time series to so-called global monsoon. That means we add rainfall anomalies that falling in all this monsoon domain. Thus, we can get a so-called global monsoon index. And here is the result. I also show the East Asian Summer Monsoon Index here. You can find in the past about 50 years, the weakening trend of the East Asian Summer Monsoon actually is a local manifestation of global monsoon. For East Asian Summer Monsoon, we know it's driven by the PDO. So PDO is also a driving mechanism for the long-term changes of global monsoon. But the question here is, in the Handcast, the prediction scale of PDO is pretty low. Here I show the result of the Peacemaker Experiment over the Eastern Pacific. Here again, we have done 3-member ensemble simulation. And here is the global mean surface temperature derived from Hadley Center HadCRU dataset. And here is the result of a historical simulation. And here is the pacemaker RAM. We can find that we do have reproduced part of the heaters, although it's still slightly stronger than the observation. Our focus here is whether the changes of global monsoon can be reproduced in this kind of pacemaker RAM. The answer is yes. Here, we show the global monsoon index derived from NSAP and also the pacemaker RAM. You can find in the past 60 years, the correlation coefficient is 0.65. After removing internal signals, the correlation coefficient is still significant. So based on this, we can say if we can get a higher PDO scale, then we can get a higher global monsoon scale. But the question here is, at least based on the result of multi-model ensemble of CMAP5, current state-of-the-art models in the prediction of PDO is pretty low. So this kind of model weakness may pose a challenge for the prediction of global monsoon. To make a summary, we have the following points. For the strength of the APGOS S2 decadal handcast, there are significant prediction skills in the Indian Ocean, tropical Western Pacific, and the Atlantic. The skills are nearly similar to the result of CMAP5 multi-model ensemble. In the model world of APGOS, the predictive skills of the Atlantic multi-decadal variability are resulted from the northward heat transport anomalies associated with the preceding fluctuations of the Atlantic meridional overturning circulation. For the weakness of APGOS handcast is that we cannot get useful skills for PDO because global monsoon, including Asian and African and American monsoons, actually are dominated by the phase changes of PDO. So the limitation of the current models in predicting PDO pose a challenge for the prediction of global monsoon. In our model result, we have two sets of simulations. One specifies aerosol optical depths associated with volcanoes to the stratosphere. Another simply changed the solar variability to represent the volcanoes, but the response are different. So it seems the skills for the decadal predictability of the Eastern Pacific seem to be model dependent. Although in both our two models, we have used an identical initialization scheme. To understand this kind of difference, we hypothesize maybe that it's due to the treatment of the volcanic aerosols in these two model versions. That's all for my talk. Thank you.
Yeah, question?
I didn't catch it. When you put in the optical depth for volcanoes, did you do it in just one or two model layers in the lower stratosphere? Did you fill up the whole stratosphere? Did you do it as a function of time of year and latitude? How did you do that?
We specify the aerosol optical depths throughout all the latitudes, mainly in the stratosphere. This is the case for APGOS S2. But for the low resolution model,
I understand, but was it the same at all altitudes and all latitudes?
yes, it's for zonal average. This is the standard data used in CMAP5.
I know it is zonal average, but in latitude was it the same? And in
No,
altitude
no,
was it
it's
the same?
latitude dependent.
And altitude dependent?
Yeah, because in historical simulation, especially the millennial simulation, we have different kinds of volcanoes, either in the low latitudes or in the high latitudes. In APGOS GL simulation, we do not specify aerosol optical depths. We only change the solar variability, so we can get predictive skill in the Eastern Pacific.
Doug?
So it's just a comment really, but it's difficult to get robust differences in skill if you've just run the core set, which is every 5 years and only 3 ensemble members. And there's quite a lot of noise in your assessment of the skills. So to say the skill's different between two different model versions, I think it's quite difficult from that set.
Yeah. In current simulation, we employ only 3-member ensemble simulations. We hope to repeat the APGOS S2 simulation by changing the aerosol optical depths associated with volcanoes and make comparison. Yeah. And also ensemble members should be increased.
I think I remember that in your amok plot, you showed anomalies that were hundreds of a sphere drift. Is that correct? And you were
amok
using that to
simulation.
explain
Let's go
AMD
back.
skill?
Should be this one?
Yeah, that third.
No, should be this one, yeah.
Yeah, so
Here is the result of 6 to 9 years, and here is the anomalies.
So the anomalies are hundreds of a sphere drift.
Uh-huh. The anomaly here is pretty weak in comparison. I should check the unit of the vertical axis. Yeah, I should check it. I'm not. Yeah.
It looks like it's the wrong scale to do something.
Mhm. The mean state is about 20 sphere drop, nearly identical to the observed rapid estimation 18.5 sphere drop.
So that y-axis must be wrong.
Oh, okay, I should check this. Yeah, this is anomaly, not absolute value. Yeah, yeah.
So I'm just wondering, model have really no drift. I know you try anomaly assimilation,
Yeah.
but model still somehow model drift during Handcast. So I'm just wondering, it's really no drift or still have some problem.
We have checked in because we have used assimilation only for the anomalies.
Yeah.
The drift is very small, nearly negligible. However, still there is some. So in the papers, we have some. In this analysis, we do not do bias correction, but in papers, we have done some minor correction. Yeah, yeah.
Any questions? Comments? No?
With respect to the last part of your talk on the global monsoons, you argue that actually the IPO dominates. But so what is the contribution of the Atlantic multi-decadal variability for the global monsoons?
At least for the weakening trend, your observation, the global monsoon has been weakening starting from the end of 1970s to the end of the last century. At least for this weakening trend is mainly driven by the PDO-like SST anomalies. But for the recent change, we know starting from the late of the 1970s up to now, the global monsoon has been recovering. For this kind of change, Professor Bin has a paper published in PNAS. He suggested it's due to the forcing of both AMO and PDO. His idea is very optimistic. He believes that in case we can predict PDO and AMO, then we can make a successful prediction of global monsoon.